Morning.
Morning.
Are we gonna cover nuclear chemistry and organic intro, like chapter 24?
Yeah,
Before the end? Okay.
yeah. Today we'll start on chapter 24, which is intro to organic and biochem. And then after we do that chapter, we'll do the nuclear stuff. Yeah, we're kind of getting to the end here.
Yeah, we're getting close. I wish organic chemistry right now was as
simple as this.
Going over carboxylic acids and proteins as a kind of intro to biochem for next semester.
Yeah.
It's crazy to think that the beginning of organic one was this.
Yeah. Yeah, as you go on and you look back at the stuff, you kind of, you have a different opinion of it
Yeah.
than you did when you first took it, so.
It's crazy how much it all builds off of every chapter in organic.
Yeah.
It's like every chapter builds after it keeps on going.
Yeah, yeah. Well, it's even that way with Gen Chem. If you look at what you learn in Gen Chem and then you look what you learn in later classes, it all links back to the stuff there.
Yeah.
It just gets into more detail and a little more, I don't know, just a little more complicated, but the basic stuff is there, so. Okay, I'm gonna go ahead and get started. Can the people on Zoom hear me and see the screen okay?
Yes. Yes.
Thank you. Okay, so what we're going to do today is I'd like to go over the answers to exam 4. And then after we finish that, we'll go ahead and we'll start chapter 24. And chapter 24 is the chapter which is kind of like an introduction to organic chemistry, introduction to biochemistry. So that chapter by no means is a replacement for organic chem or biochem, which if you stay in the science path, you'll take later on. But it'll at least get you familiar with some of the terminology and some of the nomenclature associated with those types of chemistry. So, and then the other thing I wanted to mention is next Thursday, so a week from today, we will have our final quiz, and that will be on this chapter 24 material. Okay, so let's go ahead and get started with the exam. So the first question, which element is oxidized in the reaction below? And the answer is it's the iron. You had Fe+2 going to Fe+3 plus an electron. Number 2, a reversible process is one that, and the answer is can be reversed with no net change in either system or surroundings. Number 3, the second law of thermodynamics states that, and that answer is for any spontaneous process, the entropy of the universe increases. Then number 4, what is the coefficient of the permanganate ion when the following equation is balanced? So if you went ahead and wrote out those half reactions, you'd have, and it's in an acidic solution, you'd have MnO4 minus plus 8 protons plus 5 electrons going to Mn+2 plus 4 waters for one half reaction. The other would be 2 Br minus going to Br2 plus 2 electrons. So in order to then balance the electrons out, you'd multiply the permanganate half reaction by 2 and the bromine half reaction by 5. And so you wind up with a coefficient for the permanganate of 2. The next question, number 5, what is the coefficient of Fe+3 when the following equation is balanced? And this is in a basic solution. And so if you go ahead and you balance that out, you find that the coefficient for the iron is +2. So one thing I wanted to mention is on the online version, I forgot to add the Fe+3 in there. So I want to thank Evan for letting me know about that. And I sent a message out to everyone. Hopefully everyone saw it. Most people got this right. If you did not get it right, I gave you the points anyway, because that was an error on my part. Okay, so then the next one, number 6, what transformation below is an example of an oxidation in an electrochemical cell? And the answer was NO going to NO3 minus. Number 7, the loss of electrons by an element is called, that's oxidation. Number 8, delta S is positive for the reaction, and it's the barium fluoride solid going to aqueous ions of barium+2 and fluoride minus. So the reason for that is you have a solid going to a liquid phase, so that's increasing the entropy. Number 9, for the reaction that's given there, You're given then the delta H and the delta S. And you wanted to know this reaction is, and basically what happens at different temperatures. So if you use the equation delta G equals delta H minus T delta S, we know that a negative delta G means it's spontaneous. So then if you go ahead and plug in the delta H value and the delta S value, and then plug in essentially what 0 for the delta G, and then make sure that the delta S and delta H are in the same energy units. So in other words, either kilojoules or joules, both of them. I chose to make them both joules. Then what you can see that is that delta G is negative at all temperatures. So in other words, it's negative at all temps, so that means it's spontaneous at all temps. Number 10, you're given this silver plus chloride going to silver chloride reaction, and then you're given the delta H and S values for silver ion, chloride ion, and then silver chloride solid. And you needed to know the temperature above which the reaction is non-spontaneous. So this is similar to the previous problem. So once again, you use that delta G equals delta H minus T delta S formula, set it equal to 0, go ahead and plug in the appropriate delta H and delta S values, and then you can do the problem similar to the one before. The change was you had to calculate out what the delta S and delta H values were for this reaction using these constants that were given. And so for both delta H and delta S, it's the sum of the products minus the sum of the reactants. So you'd need to go and identify which were products and which were reactants, look up their values in the table. Then you could find the delta S value for the reaction, and then you could find the delta H value for the reaction. The key there is making sure that both of those have, as above we said, have the same energy, so kilojoules or joules. And then once you got those values, you plug them into that formula as you did in the problem number 9. And then you get a value that is in Kelvin, so 1914 Kelvin. We wanted the answer in degrees C, so you needed to subtract 273 from that. And then that leaves you with 1641 as the answer. Okay, number 11, the value of delta G for a reaction is 3.05 kilojoules per mole. And then you needed to calculate the equilibrium constant for the reaction at 25 degrees C. So there you'd use the formula delta G equals minus RT times natural log of the equilibrium constant. You need to change that delta G value into joules per mole. And I did that by making it 3.05 times 10 to the third. Plug that in. Our R value constant is 8.314. The temperature is 298 in Kelvin. And then that times natural log of K. So then you're solving for that K value, and that comes out to be 0.292. Number 12, which of these is the reducing agent in the reaction below? And so if you look at the half reactions, you see that S2O2 minus 2 charge going to S4O6 minus 2 charge plus 2 electrons. That's an oxidation. The reducing agent is oxidized. So you know that the S2O3 minus 2 is the reducing agent. Number 13, needed to find the oxidation number of chromium. And so we know that the oxidation number of oxygen is usually -2. So -2 times 7 is -14. The potassium is usually +1. So we have 2 of those for +2 total. So we have -12 total there. So the chromium has to balance out with +12. There's 2 of those. So the answer is +6. Number 14. They want to know how many electrons appear in the half reactions when it's balanced. So if you go ahead and balance that, you see that there's 2 electrons involved in this half reaction. Number 15, the electrode at which oxidation occurs is called that's the thing where I said oxidation begins with a vowel, anode begins with a vowel. So that's one way of keeping it straight. So the answer is anode. Number 16, you're given some half reactions and then the potentials associated with those half reactions. And then you want to calculate out what the standard cell potential is for this cell. And then you're given the equation below. So you needed to remember that the potential for the cell is equal to the cathode potential minus the anode potential. So you needed to go through and identify from these half reactions which is the anode, which is the cathode, and then write their values in. And if you did that correctly, you would get 0.617. Okay, 17. 17, you're told what the cell potential, standard cell potential is for the reaction. That's 0.126. And you want to calculate delta G. And so that's where you'd use the formula delta G equals -N times F times the cell potential. You needed to write out half reactions to see how many electrons were involved. So you'd have lead going to lead +2, 2 electrons. The other half reaction, 2H plus 2 electrons going to H2. So it's a 2 moles of electrons. So that gives us our N value. The F value is Faraday's constant, which is 96,485. And then the potential is that 0.126 volts that we were given. You go ahead and solve that and you get minus 24,314 joules per mole. Convert that to kilojoules because that's how we wanted it, the answer expressed. And it's minus 24.3 is the value. In number 18, in a voltaic cell, electrons flow from anode to cathode. That's true. Remember, anode is where oxidation, so it's generating those electrons. They flow through the wire over to the cathode. 19, you're given a redox equation below, and you want to identify the cathode half reaction. So the cathode half reaction would be the one that has reduction, and that works out to be the 2H plus 2 electrons going to H2. Number 20, you're given information about the boiling point of methanol. And then you're told the molar enthalpy of vaporization is 71.8 kilojoules. And you want to find delta S when 1.75 moles of the methanol is vaporized at 67 degrees C. So here you have the 1.75 moles. You can multiply that by the molar enthalpy of vaporization. That's that 71.8. And we want to change that to joules. So that's times 10 to the third value, and then divide that by the temperature in Kelvin. So that's the 64.7 plus 273. If you do that correctly, you get 372 joules per Kelvin is the answer. 21. You have a pure crystalline solid that is heated from absolute zero to a temperature above the boiling point of the liquid. Which of the following processes produces the greatest increase in the entropy of the substance? So the answer is vaporizing the liquid. That's just because the gas phase has the greatest entropy. So whichever of these processes that get you into that gas phase will have the highest entropy. 22, you're given a value of delta G for the reaction given. And so you want to find delta G, you want to find delta G for the reaction that's given. You're given some information of delta H and then delta G naught. And so what you want to solve is delta G equals delta H minus T delta S. You can go ahead and plug the values in, and you're also given delta S down here. You can go ahead and plug the values into the equation. So 720.5 is your delta H. Minus 534 is the temperature in Kelvin. And then .2637 is kilojoules per mole for your changing that delta S value into kilojoules for moles. You do that correctly, you get a value of minus 597.7. 23. This is one where you needed to use the Nernst equation. So you needed to go ahead and find the half reaction so you'd know the number of moles of electrons. That worked out to be 2. Then using the Nernst equation, you have the cell potential 0.63, and then you needed to have log of Q. So that's products over reactants concentrations, plug those in, and then you can solve and get 0.51 volts. Then the last two were balancing equations. The first one is a basic solution, and you can go ahead and take a look at this, but the big thing, it seemed like people struggled a little more with the basic solution than the acidic solution. The thing to remember on the basic is you have to go ahead and you can add those hydrogens in initially. You can start it out the same way as the acidic ones. I mean, where you add water where you're lacking oxygen to that side, and then you can add hydrogens to the other side to balance out. But what you have to remember to do is, since it's basic, you got to go ahead and add hydroxides to change the hydrogen ions to water, and then add the hydroxides to the other side as well. So that was where people, I think, got hung up a little bit. But that's the main difference between the basic and the acidic ones. And then number 25, this is a real interesting one. And so want to thank Conrad for pointing out a mistake that I made on this one. So if you look at the equation as written, the first one, Cr2O7 minus, well, that's dichromate. Dichromate is a -2 charge. So when I transferred this equation from my written out test to typing it on here, I left off the -2. So one of two things could have happened. One is you could have assumed that I made a mistake and dichromate is -2 charged and solved. That's what most people did. There were 2 people in the class, one of which was Conrad, so that solved it as it's written, and it is solvable as written. You get a different answer. So if you solved it either of those 2 ways, you got credit. Okay, so I'm still trying to figure out what that means, that 2 people solved it as written and a whole bunch solved it not as written. I'm not going to think about that too much, but and some people just struggled with the problem. So, and that's fine. If you were one of those and you didn't get any points, If you solved it of one of the two ways that I just mentioned, then you got the points. So, all right, any questions about the exam? Okay, I'm going to pull up the organic chemistry stuff and we're going to talk about that a little bit today. And then we'll finish that on Tuesday. And then, as I said, we'll have the quiz on it on next Thursday. Okay. So I actually like the title of this chapter, Chemistry of Life, because really when you start talking about organic chemistry and biochemistry, you start getting into stuff that centers around medicine and nutrition and things like that, which I think most people have an interest in that kind of stuff. And it's a little more, I think it's a little more getting into like the real world than than say a thermodynamic calculation or something like that. At least I think for most people that's true. So let me hold on here. So what are we talking about in this intro chapter here? And really what we're going to be talking about is molecules that start to kind of make that bridge between chemistry and biology. So up until now, everything's been really, for the most part, chemistry focused. But this will start to introduce a little bit of how chemistry and biology link together. The most common elements are carbon, hydrogen, oxygen, and nitrogen. And organic chemistry is studying compounds that have carbon in it. It's that simple. It's always kind of funny to me because you'll hear people talk about organic foods and organic growing and all that kind of stuff. And I always find that a bit of a misnomer because to me, something organic just means it has carbon in it. And this definition was around a long time before organic gardening type of or organic food type labeling was done. So organic chemistry, when you study that, you're studying the compounds that have carbon in them. Biochemistry then takes that a step further, and it's really more chemistry around living things. And so that's where you start talking about proteins and peptides and sugars and things like that. And we'll go through some of that a little bit. What we'll be doing in this chapter is really kind of just giving you kind of an introduction to the nomenclature. And nomenclature to me is just a fancy word for the language of a subject. So anything you study, whether it's chemistry or anything else, there's just terms that you need to know. So in this chapter here, for those of you who love math, you'll be disappointed. There's no math in this chapter. For those of you who don't like math, you'll love this chapter. But what you do have to do is you have to memorize a bunch of stuff. I mean, there's really no other way around it. It's memorizing names and how we name compounds and what the definition of a certain structure is for a certain type of compound and things like that. And all that stuff's real important if you go on and take organic chemistry or biochemistry, because if you don't understand what the naming conventions are, you don't understand the language of it, so to speak, it's real hard to kind of understand what's going on. So that's one reason for having this chapter in Gen Chem is just so that as you move along, this is a first pass at it. It usually takes people a couple of tries to remember this stuff. I know it did me when I was taking it initially. And so by hearing it now, it gets you at least familiar with some of the language and some of the terms before you go on and take organic chemistry or biochemistry classes. Okay, so when we talk about organic molecules, there's a series of things here that you really need to remember. And one is that carbon will have 4 bonds to it. And depending upon how those bonds are, tells you, remember we talked about hybridization back I forget what chapter it was, but earlier in the year. If the 4 bonds are all single bonds, then you have a tetrahedral arrangement, and that's sp3 hybridized. We'll talk about, remember we've talked about double bonds in the past. If you have one of the bonds is a double bond, then it's trigonal planar, and that's a sp2 hybridized. And then finally, if one of it is a triple bond, then it's linear and it's sp hybridized. And like I said, that kind of hybridization and all that will come into play later when you start working with reactions of organic molecules and things like that. But for now in this class, I just like you to remember carbon has 4 bonds. If they're all single, it's that tetrahedral with sp3 hybridization. If there's a double bond there, one double, it's trigonal planar, sp2 hybridized. And then finally, if there's a triple bond there, it's linear and sp hybridized. The most common bonds are carbon-hydrogen bonds. And then I would say the second most common are carbon-carbon bonds. The carbon bonds are pretty stable and pretty strong. And especially when they're with another carbon, a hydrogen, an oxygen, a nitrogen, and then the halogens. Remember, halogens are the chlorine or the fluorine, things like that. There's a term that you'll use in organic chemistry called functional groups. And functional groups are just combinations of atoms that are stuck onto the molecule that have a certain property. And these functional groups are what we use to describe reactivity and things like that of the molecules. And so you'll see some examples of functional groups as we go through the chapter. And those functional groups are one of the things you'll have to just memorize. What's the definition of the different functional groups? As I said, the most prevalent bonds are carbon-carbon and carbon-hydrogen bonds. And those bonds are nonpolar. And remember, we said early on that like dissolves like. So nonpolar solvents dissolve nonpolar molecules and polar solvents dissolve polar molecules. So what that means is if it's nonpolar, it's not going to be very soluble in something that's polar. And water is a very polar solvent. So organic compounds that have a lot of CC and CH bonds are typically nonpolar and have a high level of nonpolarity to them. And so those tend to not be water soluble. This is where the functional group thing comes in. So while that base of the molecule might be nonpolar, you can put polar functional groups on it, and then that increases the water solubility and thus the polarity of the molecule. And so that's where you see, here we have an example of glucose at the top, is that in that case, you've got polar functional groups on it, and those polar functional groups kind of shift the overall polarity of the molecule from nonpolar to polar, and then you get water solubility. Because glucose, that's a sugar, so we know that's water soluble. And if you think about when we were talking about earlier about polarity and things like that, we tended to focus just on like one bond and a couple atoms and things like that. And I think I said then, but maybe I didn't, but we were looking at it on a really narrow basis. What happens is as you get to real compounds, bigger compounds, it just gets more complicated than that. So you can have portions of it that are nonpolar, but you have portions that are polar, and then you start having to evaluate the overall polarity of that molecule. And that's what will tell you if it's going to be polar or not. So we started out pretty simple, looking at 2 atoms bonded together, trying to figure out dipole moments and things like that, electronegativity. But really, now we're starting to see that it's a little more complicated than that. It gets to combinations of polar groups and nonpolar groups, and what's the overall polarity. Down at the bottom here, we have stearic acid. And what you have here is you have a long hydrocarbon chain. And then at the bottom, you have a carboxyl group. And we'll see what a carboxyl group is in a moment here. But what all this simply is saying is that the long chain is nonpolar, the end is polar. And this is real common in surfactants. And surfactants, fancy name for soap, is that what those do is nonpolar end, polar end allows you to solubilize things that are either nonpolar or polar because you've got the two sides to it. We talked a little bit about that previously when we talked about emulsification and stuff like that. So when we talk about the functional groups, some of the functional groups are acidic in nature and some are basic in nature. Carboxylic acids, and we see here it's designated as COOH. That's a real common acidic group. And so another way to draw this is if you have the carbon atom and then a double bond, say, coming out of the top, and then a single bond to the OH group, that's another representation that we'll see for the carboxyl. What happens in the carboxyl group is that proton on it can be deprotonated depending upon the pH. And how do we know when that's going to deprotonate or not? That goes back to the acid dissociation constants we talked about, I don't know, a few weeks ago. So that's where you'll get the pKa of it, and that'll give you a feel for what pH you protonate it. In other words, keep that hydrogen ion on it, or deprotonate it and it comes off. So remember, I told you before when we were talking about those acid dissociation constants, the pKa is really an important property of compounds. And here's now we're starting to see why. It links back to these carboxylic acid groups and whether the compound itself is protonated or deprotonated. When we talk about bases, we're usually talking about amines. And so here's 3 examples of amines. So NH2, NHR, or NR2. R is just a generic term for another group that has carbon and hydrogen in it. The other thing I'll point out is when we have NH2 like this, that's called a primary amine. NH with an R on it, that's a secondary amine. And NR2, that's a tertiary amine. And there's actually another one where the nitrogen is protonated, you got 4 things on it, that's a quaternary amine. So what you get used to seeing in organic chemistry is if there's an amine present in the molecule, those nitrogens have the potential for basicity, okay? And so that basicity, just as the acidity on the carboxyl groups, there's different reactions that you can do associated with those properties. And the other thing I would say is, for me personally, I'm not a big organic chemist, I'm an analytical chemist. And when you analyze things, understanding how to control the protonation of these amines and the carboxyl groups is important in doing analyses as well. Okay, so let's talk about hydrocarbons. And I think we've touched on these a little bit in the past, but we'll kind of go over this again. So the definition of a hydrocarbon means you only have carbon and hydrogen. So in other words, we don't have any of the oxygen, we don't have any of the nitrogen. It's just carbon and hydrogen. And then we categorize them by the number of bonds between the carbon atoms. So in other words, is it a single bond? Is it a double bond? Is it a triple bond? And so there's 4 types: alkanes, which are the single bonds; alkenes, which are the double bonds; alkynes, which are triple bonds; and then the aromatic ones. And when you think of aromatic hydrocarbons, think of the benzene ring, where you had that kind of sharing of electrons, where we had the pi electrons kind of shared throughout the ring. And so we're going to talk about these things here. But remember, If it's a hydrocarbon, it's only carbon and hydrogen, nothing else. Here are some examples. And so if we go over here on the far left-hand side, we have the type alkane, alkene, alkyne, and aromatic. Then we have an example name of it, ethane, ethene, ethyne, benzene. Now you'll notice with the alkene and the alkyne, there's ethylene written in parentheses and acetylene written in parentheses. One of the, I'll call it odd things about organic chemistry is that there are some older compounds that were discovered long ago that have names that I would call them nicknames almost. They're not the IUPAC official name you're supposed to do it. So ethene for ethylene, for instance, ethene is the official name. I don't know if I've ever heard anyone call it ethene. Everyone calls it ethylene. Ethyne, I've never heard anyone call acetylene ethyne. I'm sure someone does somewhere, but almost everyone else calls it acetylene for that and ethylene there. So there are some examples like that where you need to learn the common name. You kind of need to know them both. The official name, like I said, is ethene for this two-member alkene, but ethylene is what people would use. So then you have the structures here written out, and then you see kind of like the ball diagram, and then finally some bond links and bond angles and things like that. Okay, so one thing about hydrocarbons, since they don't have oxygen or nitrogen in them, so in other words, they don't have some more polar atoms associated with them, it's just that carbon and hydrogen, you're gonna have nonpolar compounds. And what that means is that they're gonna be insoluble in water, because water is real polar, but they're gonna be soluble in nonpolar solvents. And so that's where when you work with these types of compounds, you're going to be working with nonpolar solvents to dissolve them and run reactions and things like that. The melting and boiling points are determined by the dispersion forces. We talked about that earlier in the semester. And so low molar mass hydrocarbons are gases. Mid-sized molar mass ones are liquids, and high molar mass ones are solids. So here's another table that you need to spend some time understanding. On the left-hand side here, we have the molecular formulas, and it goes from C1 down to C10. Then you see the condensed structural formula next to it. This is how you would write something like this out, okay? And this implies, let's look at the C4, the butane one. So this implies you have CH3, that carbon's bonded to another carbon, has 2 hydrogens off it, to another carbon, 2 hydrogens, another carbon, 3 hydrogens. So that's the general idea behind writing out this condensed structural formula. Next, you have the name: methane, ethane, propane, butane, pentane, hexane, heptane, octane, nonane, decane. I think it was first semester that we learn these prefixes, okay? So if you've forgotten it or don't remember it, this is a chance to refresh your memory and get it back in your memory. So in other words, you should know that octane has C8 in it. You should know that nonane has C9. Decane, the dec is C10. So when you name these alkanes, that first part tells you how many carbons are in it, and then the ane tells you that it's all single bonds. Over here on the right-hand side, it's got some of that, it's got boiling point data, which just kind of reinforces that for the small ones are more volatile than the big ones. So what are some of these, whether you realize it or not, you probably use. Methane, that's kind of what natural gas is. So if you have natural gas heating, it would be that. Propane, that's if you have a gas grill, that's usually what's in there. Butane, that's what's in the disposable lighters. So if you have a lighter at home to light a candle or something. And then the alkanes, when you get to C5 through C12, so you get to these bigger ones and it goes up a lot higher than that. But the C5 to C12 ones tend to be fuel. The one that you think of mostly when you go to the pump and you see that the octane rating, octane is that C8 one. Okay, so the 90 on the gas pump or whatever, that's the octane rating. And that's telling you how much of the octane is present in that fuel. Okay, so we kind of talked about these organic compounds, and we talked a little bit about the nomenclature, but now and we showed some examples of structures, but let's talk about how we write this stuff out. So it's kind of like our shorthand way of writing out molecules. And there's several ways people do this. You can have structural formulas that show how atoms are bonded to each other. And on this one on the lower left-hand side, where we have 4 carbons. So if it's 4, it's butane. So we have butane written out, and we have it written out with the bonds fully. So we see the carbons bonded to each other. We see the hydrogens bonded to those carbon atoms. And so we've written the whole thing out there. So that's a structural formula. On the right-hand side, we have a couple versions of what's called condensed structural formulas. So you don't necessarily show all those hydrogens, how they come off the carbon. So it's kind of assumed that we know, and here's the 2 versions. On the top, let's look at the bottom version first. We have CH3, CH2, CH2, CH3. So that same butane molecule, but by writing CH3 that way and then CH2, CH2, we're implying that those hydrogens are bonded to the carbon and would look like what we drew on the left-hand side when we drew everything out. That's probably the one on the bottom on the right is probably the most common way people write stuff out. The one above it is another way people will do it sometimes, where here they show the carbon bonding. So they show that each of those carbons are bonded to each other. You can do that also. And if you notice on the left-hand side here, the H3 is flipped over so that the carbon looks like it. Some people do that, some people don't. That's probably, that's done sometimes. It kind of depends on how complicated the structure is. But these are the ways that people will draw molecules out to represent how things are attached. And you could say, well, why don't you just write the molecular formula? Okay, and we could do that. We could write the molecular formula for this. But as you'll see in a little bit later this morning, the problem with molecular formulas is they don't account for isomers. So yeah, then you know how many carbons are there or how many hydrogens, but what you don't know is how's the bonding taking place? What's bonded to what or whatever. And like for this one, we could write another structure than this one for this exact molecular formula. So that's why the molecular formulas, while those are great for calculating molecular weights, they don't really tell us how things are bonded to each other. And that's where the isomer thing comes in. Okay, so let's talk about alkanes a little bit more. As we said before, in an alkane, remember everything's single bonded. So we have the sp3 hybridization, it's tetrahedral, and the bond angle is 109.5. So we see some pictures here on the right-hand side the top two. So the top one, we see what that bond angle is. The next one, we see that hybridized orbital around the carbon. And then we see that bonding of the carbon and the hydrogen. So hopefully those things look familiar. We've covered that earlier this year. And so that's an example of just the basic of the way alkanes look. The ones we've looked at so far have just been what's called straight chain alkanes. So in other words, carbon to carbon to carbon just in a row, just in a straight chain. We said that carbon atoms want to make 4 bonds. So you can have a carbon atom not just bonded to 1 or 2 carbons, but it actually can be bonded to more than that. It can be 3 or 4. And that's where we start to things get a little more complicated. The other thing is, as I said before, when we start getting away from that straight chain, we can have the same molecular formula, but now we start getting what's called branching. And then that results in what's called structural isomers. There's a couple types of isomers that we'll talk about. One is structural isomers, and this is what we're dealing with here. There's something called optical isomers, which we'll get to a little later. So when you think of the term isomer, it means, in this case, structural isomer means the molecular formula is the same. So in other words, the number of carbon, in this case, carbon and hydrogen atoms is the same, but the structure actually is different. And when the structure is different, then that leads to some other things that we have to consider. So structural isomers are possible when we have some formulas that can give us the straight chain molecule or have some branching. Okay, so structural isomer, same molecular formula, but now the way the molecules are assembled, or whether the atoms are assembled in the molecules, are slightly different. So let's take a look at a couple of these. So here on the left-hand side, we have the name of the compound. So the first one is butane, or N-butane. The N tells us that it's a straight chain. And so if we write that structural formula out, it's what we saw before. It's just the 4 carbon atoms attached to each other. And if we write that condensed, then it would be the CH3, CH2, CH2, CH3. So, okay, so that looks like what we've been seeing before. That same molecular formula, okay, is still C4H10. We can write it as 2-methyl-propane, or isobutane is the common name, but we'll go with 2-methyl-propane here. And let's look at that structural formula. We have a CH3, then we have a carbon with a hydrogen on it, and then now another CH3 group coming off of it, and then finally a third CH3 group. So it's a little easier, I think, to see on the condensed structural formula to compare the two. So what we see is we've taken one of these CH2 groups, and now we put it on this middle CH2. So that becomes then CH, and then the CH2 is written as CH3 now. So once again, molecular formula C4H10, but if all I told you was C4H10 and said draw the molecule, well, you'd say, well, do you want N-butane? Or do you want 2-methylpropane? It's either one would be correct, right? That's why drawing these structural formulas or the condensed structural formula is important, because this allows us to now see that, oh, these are 2 pretty different molecules, okay? And so because of that, we want that additional information. And Structural isomers are something that you deal with all the time. And you can do that pretty much once you get to C4, you can pretty much do that with the rest of them. There's always isomers there because you can start having those methyl groups and moving them around and things like that. And we'll see that a little bit more. So let's talk about naming organic compounds. So when we name these organic compounds, there's always a prefix, a suffix, and then the base of it. The base, and in the name, it'll just be in that order. It'll be prefix, base, and then suffix, as we see in the little diagram here. You always start with the base. The base tells you how many carbons are in the longest part of the chain. So you got to look at the molecule, you got to draw it out, you got to look at it and kind of, it's almost like a connect the dot thing, is what's the biggest connect the dot I can do. And that'll tell you, is the base 6 or 7 or 8 or 3 or whatever. Then once you get that kind of core of it, the base, the spine, however you want to think of it, then the prefix tells you what groups are attached, okay? Maybe it's an OH group, maybe it's an NH group, double bonded oxygen, whatever it is. Then you start saying, and you'll number the carbons starting at 1, 2, 3 on down the line for whatever that base is. And then you'll start saying what groups are attached and where are they attached. And then finally, the suffix tells you what type of molecule it is. Is it an alkane? Is it an alkene? Is it an alcohol? Is it whatever that is? So by having this base, which is telling us how many carbons are in that longest chain that I can find, the prefix, which tells us what things are coming off of that, and then the suffix, which tells us what kind of grouping or what family it's from. Putting those three things together is the basic idea of how we name compounds in organic chemistry. And that's where the memorizing stuff comes into play, okay? I don't think anyone is born knowing how to name organic compounds. You just have to kind of learn the process and learn the definitions of some things. Okay, so let's take an example here. So on the right-hand side, we have a structure, and we're gonna look at how that would be named. So as I said, the first thing you want to do is try and figure out what's the longest continuous chain of the carbon atoms you can come up with. And in this one, we have them labeled 1 through 6, okay? And just one thing, in case you're wondering, we have the CH3 group on the right-hand side labeled 1. It just as easily could have been the CH3 group on the left-hand side labeled 1, okay? Either one would be fine. In each case, you'd still have 1, 2, 3, 4, 5, 6 carbon atoms, okay? And so because 6 carbon atoms is our longest chain, that's where the hex, so then this 2-methylhexane, that's where the hex comes from. Hex is 6. Remember I talked before, we needed to learn hex is 6, hept is 7, oct is 8, those things. We learned those earlier in the year. If you've forgotten, you need to go back and refresh your memory. So that's where the hex comes in, because 6. If we look at, let's stick to the convention, the 1, 2, 3, 4, 5, 6 convention that we have in our picture. We see this CH3 group, so that's a methyl group. That is on the number 2 carbon, right? So we want to say there's a methyl group, so that's why we have methyl here in the name, but we want to tell people where it's located. And you always do this so that it's the smallest number. So that's why we didn't start where the 6 is and call that 1 and then the 5, 2 on down the line. So because this is the smallest number by starting 1 at the end that we did, then 2 is where the methyl is at. So that tells us the location of the methyl group is at the 2 carbon. So we get 2 methyl. So we got 2 methyl, we got hex. The last thing is the suffix, the ane, ane. That tells me that it's all single bonds. It's an alkane, okay? So that's the logic you use in trying to name these. So once again, just kind of talking about that. We look at the molecule that we've drawn out. We try and find the longest continuous chain of carbon atoms. Then that gives us that base. In this case, it was hex for 6. Then we go and we look at where functional groups are coming off of our base. In this case, we had 1. We had that methyl group, that CH3 group. And we said, okay, if we started naming that convention with 1 up there, that gives us the lowest number. Gives us a 2, whereas if we did it the other way, it would be a 5. So it's not 5-methylhexane, it's 2-methylhexane. So then we found, in this case, we only had 1 functional group coming off, the 1 methyl group. So we've got that. And then finally, it's all single bonds. So that's the alkane. So it has the ane as the suffix. Okay. So this is a pretty simple one actually to name. There's others that are more complicated, and we'll go through some of that. And there's some homework problems as well that you can work on. But this is the general idea of what we do when we name a compound. Okay, so let's take a look at some of the common alkyl groups. So remember I said the CH3 group coming off in that example we just did, that's a methyl group. Well, there are some other common ones that people have. So CH3CH2, that's an ethyl group. CH3, CH2, CH2, that's a propyl group. 4 is butyl. Then it gets a little bit tricky. Now you have something called isopropyl. Okay, so isopropyl, same as our propyl, it's 3, but now you see here, we're attaching to that middle carbon, not an end carbon like we did in the propyl up above. Okay, so that is, this configuration here is called an iso group, in this case isopropyl, because there's 3. And then finally, tert-butyl. Tert is tertiary. Tertiary means 4. So we've got 4 carbons here. We've got a configuration where the 3 CH3 groups come off that other carbon, and then it'll attach to something. That's called a tert-butyl or T-butyl group. So, like I said earlier, there's a lot of stuff to keep track of. The goal isn't for you to be an expert in this when you leave this class. The goal is to get you starting to see this so that in the future, as you hear more about it, it won't be the first time you've heard it. Okay, so let's try another naming of one that's a little more complicated, okay? And so in this case, we see down at the bottom here, the name of the compound is 3-ethyl 2,4,5-trimethyl heptane. Boy, that's a lot going on there. So what do we do? Well, once we get over kind of the shock of how many carbon atoms are floating around here, we go back and we think of this once again as kind of that connect the dot puzzle of where we're looking through this and we're trying to see what's the longest chain of continuous carbon atoms can we kind of trace through here with this molecule, okay? And so we've got that in the box, okay? And if you don't think it's right, you can spend some time later seeing if you can come up with a longer one, but I'm pretty sure it's right. And what you see is we can actually link together a series of 7 carbon atoms as our longest continuous chain. And so then that's where the HEPT comes in. The other thing that we'll just get out of the way right now is it's all single bonds. So it's the ane, A and E, the suffix. So we've got heptane there. Well, now it gets a little where we got to make some decisions on what groups are coming off of it, off of that base chain, and where are they located. So the first decision we have to make is, which do we call the number 1 carbon? Do we call this one on the bottom here, that CH3, that carbon, the number 1, or we call the CH3 carbon up on top the number 1? Well, let's go and see here. 1, 2, 3, if we start from the top. Then we have, if we start from the bottom, we have 1, 2, and 3, 4. So we're going to want to have the 1 carbon down at the bottom, because then that gives us something off the 2. If we start with this CH3 that's labeled 7 as the 1 there, then we don't have anything on 1, we don't have anything on 2. It's not till we get to 3 that we have something. Starting with the number 1 carbon at the bottom, we have 1, and then on 2, we start having something. Remember, we want to go with this in a way that gives us a functional group and one of these alkyl groups coming off at the lowest number. So we figured that out now. So we agree that this is the correct carbon to call carbon 1, this CH3 carbon down at the bottom. And so now we need to see, well, okay, we drew our little box to make it clearer for us to understand what the base of the molecule is. What do we have hanging off that base? Well, let's look at the 2 carbon. We have a methyl group there. Okay, so we have a 2-methyl. Then we look at the 3 carbon. We've got a CH3CH2 group there. So that's an ethyl group. Okay, so we got an ethyl group coming off the 3 carbon. We go to the 4 carbon. We've got another methyl group coming off there. 5 carbon, a methyl group there. So we've got a 2, a 4, and a 5. So we've got 3 methyl groups coming off there. And then we've got an ethyl group coming off the 3 carbon. So we know it's going to be 2, 4, 5 for the methyl. And since there's 3, we say tri. So we get 2, 4, 5 trimethyl. And then we know there's a 3-ethyl. But how do we decide, does it go 3-ethyl or do we do the methyls first? Because the methyl's got a 2 on it, so the number's less. Well, the way you do this is it's alphabetical. And you don't count the tri part. It's just the ethyl versus methyl. So E comes before M, so that's why the ethyl is written, the 3-ethyl is written first. Okay, so it's kind of being polite. You're doing an alphabetical order. So then with that, we wrap that all together. We have 3-ethyl, 2,4,5 trimethyl heptane. So once again, remember when we were trying to figure out how to name this compound, we tried to see how those carbon atoms connected, and we tried to figure out what was the longest continuous connection we could make. In this case, it was 7, so that's the hept part. Everything's single bond in that chain, so it's an ane, heptane. Then we look at what's coming off that chain, and we identified 3 methyl groups. So remember, methyl is CH3. We identified 3 of those, and we identified 1 ethyl group, 1 CH2, CH3 group. So we had 4 things coming off. Then we had to figure out, well, what's the location? And that goes back to figuring out which end of that base chain is number 1 and which end is number, in this case, number 7. And we figured that out by looking at it, which one gave us the lowest number starting with something coming off. In this case, we had a methyl group coming off 2. If we start as 1 as that bottom carbon and the bottom CH3. So once we did that, then we could count up our methyls. We had 3 of them, so that's trimethyl. We now have the locations, 2, 4, 5. And then we have one ethyl group, so ethyl, and that's located at 3. And then once again, the final thing was to check, okay, which one goes first, ethyl or methyl? E in the alphabet comes before M, so the ethyl goes first. So, okay. So a lot of thinking we had to do. Yes?
Do you want to minimize substituents? Like when you pull that out, it looked like 3 isopropyl, 4 or 5.
3 isopropyl.
If you start at the ethyl group.
Yeah, I think the reason why you don't do that is you want the longest chain.
Yeah, it still produce heptane. If you go where off the CH3 off the apple.
See. So here, this would be then 1,
Off the
2.
off the CH3 to your, there you go.
This one?
Yeah,
So you're saying, what are you saying here?
start there and go left.
1, 2, 3, 4, 5, 6, 7.
Yeah, that's your chain.
You get that, and then you have an isopropyl here off of the 3. And then,
4 or 5 dimethyl.
yeah, you could probably do it that way too. Yeah, you could do it that way too.
Yeah, I just didn't know if you had minimized substituents on that.
I'm sure there's some organic rule on that. I've forgotten. Yeah, I think you could do that either way. I'll have to think about that. But this is why naming organic molecules, people argue about this stuff.
I can see how.
And so, and for me personally, I never had any interest in arguing about it. So it was like, whatever. The key is we know what it is. We can draw it out. Okay, so let's talk a little bit more about alkanes. So alkanes really don't react much. And that's because they're nonpolar and those CC and CH bonds are pretty stable. They're sigma bonds. You think of sigma bonds usually don't react a lot. So they don't really react with acid bases or oxidizing agents, but what they do is they combust. And if you notice when we talked about those uses for the alkanes, they almost all of them, I think, involved burning, okay? And burning is what we're talking about with oxidation reactions. And so here's an example oxidation reaction here for ethane. And you see its delta H is exothermic, and it's a pretty good size number. So that's the one thing and one reason why people have a lot of interest in alkanes, and this goes back to the whole petroleum industry, which is the source of most of the alkanes, is that these can be burned. It's an oxidation reaction, and you can get heat, fuel, things like that. Okay, so when we talk about hydrocarbons, if we're talking about things that have single bonds, we say they're saturated, and that's the alkanes. And what the saturated means, does each carbon have the maximum amount of hydrogen on it? So you hear about saturated fats a lot of times. That's not exactly, it's not an alkane necessarily that you're worried about there, but you think of saturated fats. Those are the fats that have all the hydrogens you can have. And so that's the same with these alkanes, is that if we look at an alkane, each of those carbon atoms has the maximum number of hydrogens. So we call that saturated with hydrogen atoms. When we get to the alkenes, the alkynes, and the aromatic, we have fewer hydrogen atoms than the alkanes would be, but the same number of carbon atoms. This is called unsaturated. So in other words, instead of having the maximum number of hydrogen atoms, in these cases, you start to have multiple bonds, double bonds, triple bonds, things like that. And so things that don't have that maximum number of hydrogen are called unsaturated. The unsaturated hydrocarbons are more reactive than the saturated ones. And that's because when you start to get that unsaturation, you get that because you start having the pi bonds. The saturated ones are just the sigma bonds, which we say aren't very reactive. Now, when you start getting double, triple bonds, things like that, that's the pi bonds, and those pi electrons, you can do more things with those. Okay, so I'm going to stop there because the next thing is to start talking about alkenes, and I don't have enough time to finish. So I'm going to stop there, and then we'll continue on with this and finish it up on Tuesday. And then, as I said, next Thursday, we'll have a quiz on this chapter next Thursday. Okay, any questions about anything? All right, thanks.
Question about the test.
Uh-huh.
Well, let me pull it up real quick. Okay, it was question 6, which was the oxidation in an electrochemical cell.
Uh-huh.
Would be, because it says oxidation is losing electrons, but C goes from no charge to -3. So wouldn't that have gained electrons?
So you have to write out the half reaction to see what the electron is.
Okay.
I'm writing it out now to see what it is exactly so I can tell you. Okay, so if you write it out, then you have, you would add 3 waters, or rather 2 waters to the left side. Okay, so then that balances your, that balances out your oxygens. So you have 3 oxygens on each side, 1 nitrogen on each side. And then on the right-hand side, you'd add 4 protons to balance the 4 hydrogens out. So then you wind up with a net +3 charge on the right-hand side. So then you'd have to have +3 electrons on the right-hand side to balance out the charge, to have 0 on each side. So if you have the 3 electrons on the right-hand side, that means it's an oxidation.
Okay, so you just have to like write out the whole equation and balance it.
Right, yeah. So it's not just looking at the charges on the molecules or ions and looking at that. You have to write out those redox half reactions and find which one was an oxidation. So in other words, which one winds up with some number of electrons on the right-hand side.
Okay, that makes sense. Thank you.
Okay, you're welcome, thanks.